Okay, now we are starting to get into exercises that are a little bit more complicated. So just a second. Okay, now we need to find the value VC, and I lost my notes, I think. I'll pause here for a second, sorry about that. Okay, I lost one of my notes for this exercise, but don't worry, we can do it on the fly, it's fine. I only have a little bit of the first part of it. Now, let's see, what can we do? Well, first of all, we can transform this. We can say that this voltage is 10 volts. Instead of being connected to this wire here, we can connect it one here, so there'll be 10 volts to here, and the other one here, so there'll be 10 volts to here as well. Okay, and what else can we do next? Well, we can also move it down here. Okay, and then we can write it as this. It starts with 10 volts and it's got a resistance here going through here, instead of having this part here, and this one will be 2.2k ohms. There you go, and we made it a lot easier. Now now that we make it a lot simpler, and you may also notice this circuit because you should use this kind of circuits, transistor circuits, on amplifiers. But okay, so because of this circuit here, let me get the red one. Something that we can do to simplify it is we can apply Thevenin's theorem. We can mark one point here and one point here and say Thevenin's theorem, TH, okay? And now we just calculate the values of TH. And if you don't know how to do Thevenin's theorem, then look at one of my older videos. It's quite simple, it's similar to superposition, but I'm not going to spend a lot of time explaining it here. Okay, so Thevenin's theorem, we can see that those resistors here are in parallel. So then RTH will be equal with 2.2k parallel with 10k, and that will be equal to 1.8k ohms. Next one that we need to find is VTH, the voltage going through it. So VTH, and that will be equal with, and we can apply, we need to find at this point here, so we can apply the voltage divider rule, so that will be 10k times 10 over 2.2k plus 10k, okay, voltage divider rule, let's put rule as a rule, and that will be equal to 8.2 volts. Alright, so we have the RTH and we also have the voltage. Now this is the part where, yeah, the exercise cuts, so I don't have the notes for it, but don't worry, I won't leave you like this, we'll finish it. So because we know these two and we replace the circuit from this side with an RTH circuit, then we can redo the diagram like this. There will be the 8.2 volts coming as the input, there will be the resistance of 1.8k ohms, okay, then there will be this one with the point I, E, and the resistance again with the 10 volts at the top, and this one will be 1k ohms, and at the bottom here another resistance with the ground, and that will be 3.6k ohms, because remember we only change this section going that way, so we only have this one for the base. Let's mark it as well. That will be the base, emitter, and collector. And remember that the gain on this one is given to us, so that will be 100. Okay, first things first, let's mark the currents. So like the previous exercise, there's one current going this way, the IE, current going this way, the IC, and then current going this way, the IB. Alright, so the way we can do it is we can draw it something like this way, and then this way as well. Okay, this should be correct. Next step will be to calculate IB, because we can do that quite easily. So because we got 8.2 volts, 8.2 minus 1.8k ohms. Okay, so it goes to the IC, so that'll be minus 0. BC. Let me check the rules. Base collected, yeah, there's no current going through it. Okay, so I need to use the E value. Okay, so that'll be minus 0.7 minus 1k ohm. Okay, so it's not that side, it's this side. Okay, times, it's 100, so that'll be 101 minus 10 volts. All right, so then we should get something like, oh wait, this one is IB and this one is IB. Okay, so then that would be 8.2 minus 0.7 minus 10. Okay, that would be 2.5. 2.5. I put it positive because I put it beyond the 0. There you go. And for the ohms, so that'll be 1.8k ohm IB minus, that'll be 101k ohms IB. Okay, and then therefore IB would be equal with, let's see, so it'll be 2.5 over, that's a minus here as well, that'll be 102.8 times 10 to the 3, and then that will be 24.32 microamps. 24.32 microamps. Okay, and this seems correct, to be honest. Yeah. Alright, now, but something else doesn't. Is it like really 2.5? 2.8 minus 0.7 minus 10. Yeah, it is 2.5. Strange. Okay, so that's the IB. Now that we know IB, we can easily find the other values. And remember, we only need to just find the VCE. Okay, so we can find the drop from this voltage, the VE. So then that would be 10 minus 1k ohms times 24.32 microamps multiplied by 101, and that will be equal with, see here, so that will be 10 minus 1k times 24.32 times 10 to the minus 6 times 101, and that will be equal with 7.544, I guess, volts. So that's the value for VE. Now what we need to find is the value for VC, which would be this one here, VC. Alright, and we kind of apply the same thing really. So that would be 0, and that would be the value of IC. So what would it be? It'd be like just, no, the current goes downwards, goes this way, so it should just be the IC value here. So that would be, so VC will simply be equal with 3.6k ohms times IC. Now let's say that's 100 IB, and that's equal with, let's see here, so 3.6 times 10 to the 3 multiplied by 100 times that will be 24.32 times 10 to the minus 6. Okay, and that's equal with, oops, there you go, 8.755. So let's say 8.755 volts. So this will be VC. All right. Now VCE will simply be equal with VC, which is VC minus VE, and that's equal with 8.755 minus 7.544, and then that one will be equal with 8.755 minus 7.544. That'll be 1.211 volts. Quite a low voltage drop, but that's fine. I guess we could check it. We could do it in this way. So we can do 10 minus 1 times 3 times 101 times 24.32 times 10 to the minus 6, okay, minus 1.211 minus 3.6 times 10 to the 3 multiplied by multiplied by 24.32 times 10 to the minus 6, and we got the wrong answer. Okay, so 10, that's minus 1k times 101 times 24. Oh, I forgot to do the times 100 here that time. Okay, times 100 times that value. It's still wrong, it's minus, then it's minus 2.45. Okay, so 10 minus 10, 24, and then, sorry, my sister was like, 1.211. So that will be this value here that we just find out, minus 3.6k times 100 times 10 to the 10 to the minus 6. Okay, is it actually correct? He's supposed to give me 0, meaning that I did one of the calculations must be wrong then. But where and which one? Okay, what if I do it the other way around? What if I do 0 minus 3.6 times 10 to the 3 times 100 times 24.32 times 10 to the minus 6 minus that's 1.211, okay, minus 1k times 24.32 times 10 to the minus 6 minus 10, and that time it's only minus 20, which is even worse. Okay, I wonder why though. Why do I get the wrong value? Okay, so it's going in this way. We got the, okay, so we got the 10. I guess I should have started the 10 in here, and maybe that's why. That might be the reason actually, and that's a bit annoying. Anyway, okay. No. Maybe, no. Even if I did the other way around, it will still give me the same answer, wouldn't it? Yeah. Even if I did it in this way, I have this one circled this way, it still be the same answer. Because it'd be 8 minus that stuff going round. Okay. And then this one would start from 10, that'll be minus 1k times 24, okay, and that would give me 7.544. And then to point C, it will actually go up to 8.755. Okay, so maybe it's not minus, maybe it's plus that value. So let's try that way. Yeah, so 10 minus, what is it, 3 times 101 times 24.32 times 10 to the minus 6. Okay, and then it will be plus 1.211 minus 3.6 times 10 to the 3 times 100 times 24.32 times 10 to the minus 6. I mean, it is a lot smaller. I mean, I guess I'll take it because it's close enough. I don't know, honestly. I'm not sure what I did wrong or where did I go wrong on this one. Anyway, I mean, if you want, you can try it in the comments and tell me where I went wrong with it. But I'm pretty sure this is how I'm supposed to do it. Maybe I'm just missing something here that I'm not noticing. Yeah, but anyway, what you need to understand is that we can move this side, this is the here, in this position here. That will make it easier to calculate the Thevenin's theorem, and then make it in one byte here, in one section here. Don't worry, the next exercise will be a lot easier. Even though it will be similar, it will be a lot easier because this is also a bit confusing because it's not only that's upside down, but it's an upside down NPN as well. So yeah, I don't know, and I guess this one was supposed to be a minus value, but I'm not sure about that either. I might be just entirely wrong about this one. But anyway, as I said, just tell me in the comments whether you think I went wrong on this one, to be honest. Okay, I'll pause here, I'll stop here, and I'll see you in the next exercise. Alright, now this one is the next one. This one is a lot easier. It's not an NPN, it's an PNP. And we just need to find all the values, meaning that we need to find all the currents and the voltages. So because, like, let's see, not the blue one, this one. So we also need to find VB, we need to find VC, and also VE. And we also need to find the currents IB, IC, and IE. Okay, alright. Now, let's see. How do we start? Well, we can start with the loops, like usual. So one loop here, and one loop here. Okay, and we just apply our method. Because we can actually find IB, surprisingly enough, by just using IE from here, and I guess we should do that. No, actually, let's do it a bit different. So let's find first IE, and then we will use the alpha to find IB, because I don't really get the occasion that often to use alpha. So that'll be here 4 volts to go in this direction. It will go through it, so that'll be minus 0.7, and then it goes down through RE, so that will be minus 3.3 K IE, and that will be therefore 3.3 volts over 3.3 K. That will be equal with IE, and that's equal to 1 milliamp. Alright, very nice. Next will be the next part thing we can do next is find alpha, and we know the gain, it's 100, so we can do 100, and we know IE, it's the gain plus IB, so that'll be 101, and therefore now that will be equal with 0.99. Right, now let's see here, IC, we now can find it out by doing IE multiplied by 0.99 by the alpha. Therefore IC will be equal with 1 milliamp multiplied by 0.99, and that's equal to 0.99 milliamps. Okay, next step therefore will be to find IB, because we need also IB. And you may see like this is weird, like the first current that we found is usually the last current, which is IE, and then we found IC, which is usually the second current, and now we lastly find IB. It's kind of like calculating backwards with the alpha, but again, it gives you the advantage in case you cannot calculate the IB, in case there was like no resistance here as well, and the only thing you had to go on was IC or something like that. Okay, so IB now be equal with 0.99 milliamps over 100, and that will be equal with 9.9 microamps. Right. Then VE, because we need to find the V voltages as well, VE, this one here, we can say this VB minus VBE, and you'll see what I mean by that in a moment. It's equal with VB minus VBE. Okay, because there is no resistance to it, then VB will automatically be equal with 4 volts, because again there is no resistance, and VBE, we know that to transition it takes 0.7 volts, so then VE would simply be equal with, therefore VE will simply be equal with 4 minus 0.7, which will be equal to 3.3 K. No, 3.3 volts, okay, sorry. And if you don't trust me, what we can do is simply just do 3.3 times 1 milliamp, and that will give you 3.3 volts as well, because you just calculate it, we can like use it that way. Okay, now next what we need to find is VC, and finding VC, it's easy as well. So then VC will be equal with, let's do it this way, and we can't calculate it because there's no transfer between VB and VC, so we can't do VB minus VBC, so we have to use the resistances this time. So now VC will be equal with RC times IC, and that will be equal with 4.7K ohms multiplied by the 0.99 milliamps, basically the alpha, now the current we got from the alpha, and that will be equal with 4.653. okay, but remember this one is a voltage drop at this point here, that 4.653, and we need to find this VC. So another step that we need to do is we need to do VC equal with 10 minus 4.653, and then that one will be equal to 5.347 volts, and that will be the voltage. So that way we found all the values, we have found all the voltages, and also we found all the currents. Quite simple and quite quick, and I think it's a lot easier to calculate when it comes to PNPs instead of the NPN, because it's just more like easy to understand and easy to follow, and the ways I'm more used to this type than the other, and also it's because it's not flipped upside down either. I think when you put the emitter on the top and the capacitor on the bottom, you'll just confuse a lot of people with that one. But anyway, thanks for watching, and I will see you in the next exercise. Bye. Again, now let's do another one of those examples, and this time it's just for practice purposes, like just to practice a little bit more, see how fast we can solve it actually. But anyway, so 3 points here, VB, this one will be VC, and this one will be VE. One loop here and one loop here, and we need to find the currents as well. Okay, VB, so this one VB will be equal to 6 volts, there's no resistance going through, and there will be 0.7 volts for the transfer. So to find IE, we can do 6 minus 0.7 minus 3.3 K. IE multiplied by IE, therefore we do, that will give us 5.3 minus 3.3 K IE equal to 0. Therefore, IE will be equal with 5.3 over 3.3 K. And then that will be equal with 1.61 milliamps. And VB will be equal with 6 volts, because as we said before. So now we can discover VE by simply doing VB minus VBE, and that will be equal with 6 minus 0.7, and that's 5.3. Alright, we already found half of them. Now we can apply the alpha, and that will be equal with 100 over 101, because you know that again it's 100. Again, that will be 0.99. Therefore, IC is equal with IE multiplied by the alpha. Therefore, IC will be equal with 1.61 milliamps times 0.99. And then therefore, IC will be equal with 1.59 milliamps. Okay, so now we found the IC. Now what we need to do is to find IB. And IB will simply be equal with, we can do this value, 1.59 milliamps divided by 100. My god, it's been so long since I did this sign, because I'm so used to do fractions now that I really see doing this sign. But anyway, divide by 100, and that's equal with 15.9 microamps. And the last step will be to find VC, which is equal to 10 minus 4.7K, this value multiplied by the current, times 1.59 milliamps, and that will be equal with 2.53 volts. And that's the final answer, and that's how you find all the values again for the same problem. It's not a shame to like do the same problems like 2 or 3 times, just to like try to get them and memorize them in a way to better understand their formula. Just do minor changes. Just change the choice here to from 6 to something else, or change this one to 5K or 6K or so on, and redo the calculation and see if you get the right answer or not. And again, like the way to check if you got the right answer, just use the calculator for it. Just do like 10 minus 4.7K times the 3 multiplied by 100 times, what was it, 15.9 times 10 to the minus 6. Okay, and then we take this on away. Oh, we don't know VCE. Oh, well, we know VC, that's 2 point, yeah, we can do it like this. So that'll be 2.53 minus E, which is 5.3, okay, minus 3.3 times into 3 multiplied by, again, 15.9 times 10 to the minus 6. Oh, and let me not forget the 101. Okay, multiplied by that value. It's minus 10. Oh my god, not again. Okay, that's K. Okay, that's 100. Let's see. So that's 114 point, let's see here, no, it's 15. Okay, but that shouldn't make a big difference. 15.9. okay, minus 6, yeah, the micro, minus 2.53 minus 53, okay, minus 2.53 minus 3.3K times 101 divided by 50.9. Okay, why though? Did I do it the wrong way around? I mean, I could try the other way around. I could try, yeah, let's try it that way. So 0 minus 3.3 times 3 times 101 times 15.9 times into minus 6 okay, minus VE that would be, okay, let's see, that would be 53, 5.3, and then minus, but down the minus, let's try with the, yeah, let's do minus 2.53 minus 4.7 times 3 multiplied by 100 times 15.9 times 10 to the minus 6 minus 10. That's minus 30 now. My god. 25. I know these are the right answers, right? I know for certain these are the right answers. Because this one is an example from one of my teachers' classroom examples. He used this problem to give us as an example in the classroom. And I know for sure this is not wrong. These are the solutions for it. Okay, let's try to calculate VCE. Okay, so then VCE. I can't believe it. Like, this was supposed to be fast. It wasn't supposed to take so long. Okay, so VCE, that'll be VC minus VE, and that will be equal with 2.53 minus 5.3. Maybe that was the mistake that I did. That will be equal with some 2.53 minus 5.3. That will be equal with minus 2.77. Alright. So then 10 minus 4.7 is the 3 multiplied by 15.9 times 10 to the minus 6. Okay, so minus and minus, that will be a plus 2.77. Okay, minus 3.3 times 10 to the 3 times 15.9 times 10 to the minus 6. That's 12 now. Anyway. Alright, now for this exercise, this time we are using AC input and an AC output. And don't worry, after this one, I think we got only 1, 2, 3, 4. I got 4 more exercises. Anyway, and yeah, so let's get started. I guess we can. I guess I'll explain. Sometimes I feel tired from like doing and recording so many of them in so much. Anyway, first we can get rid of this wire because there will be 12 volts at this point and 12 volts at this point. Again, I usually cut the wire because it's useless, since this one here is the base, this one here would be the, so the base goes here, this one here would be the collector, and this one would be the emitter. Because there's no current going through the base and collector, this wire would just make things more confusing than easier, you know. Anyway, so yeah, first step, let's see. So I'm sorry, there's a red one. 12 volts is coming from this point, it's coming down in this direction to IB, and then going inside the transistor, which will go to the emitter. So we can say that 12 minus 0.7, the voltage here, 0.7 minus 240k IB will equal to 0. Therefore 11.3 minus 240k multiplied by IB, that will be equal to 0. Then therefore IB will be equal with 11.3 over 240k, and that will be equal with 47.08 microamps. Alright, so now we find the current IB. We know the gain is 50 for this transistor, so we can easily find IC by simply doing 47.08 multiplied by 50, and that will give us 2.354 milliamps. And VCE would be equal with 12 minus 2.2k 2.2k, because that's the point we want to calculate. The 2.2k, it's coming from the collector down, so that will be times IC, wait, so 2.2k times IC, okay, and then therefore 12 minus 2.2k times 2.354 milliamps, that will be equal to 6.82 volts. Alright, so that's the voltage we gave for VC. Now, what if the gain B was actually equal to 100? Well, it's very simple. Instead of using IC, we can just use 100 IB. So what we can do, IC equal with 47.08 micro times 100, and that's equal with 4.708 milliamps. And then VCE will be equal with 12 minus 2.2k times 4.708 milliamps, and that's equal with 1.6424 volts. What I wanted to show with this if statement is that even if we change the gain to something new, the base current, at least in this here, will still remain the same. And also the point of this AC output and AC input is that they are separated by a capacitor, and because it's a capacitor here, then when it's charged up, current simply cannot go through it, so it will force it to go through here. The point of using the VCC here is to boost up the signal. Instead of being at the base level, the AC signal, because of that DC input of 12 volts, let's say it was around here, then it will be, oops, let's say it's bigger, I guess, there'll be something like that. It will basically be at this point here, instead of being at these points here, to just be higher. Alright, so this one was this exercise. Again, another simple one. Even though we got AC input and output, it doesn't really affect the circuit since they are separated by the capacitors. Alright, let's go to the next one then. Okay, this one it's an amplifier formation, and I'll show you why this is special compared to the other transistors that we did so far, especially because of this component, and why in transistor amplifiers we do use this component. Okay, so let's get started with the blue one to mark what we know or what we can do. So we can cut off this here, we get 22 volts here and 22 volts at this point here. Okay, and we just got rid of the wire, and we can move it downwards here. You can see that there's 22 volts here, a resistor here connected to there, and this resistor will be the 39k. Okay, what we do next, this time with the red one, as the previous example, we mark the 2 points and we apply Thevenin's theorem here, TH, to make the circuit smaller and shorter. So then what we need to find is the RTH, and that will be simply 39k in parallel with 3.9k, and that will be equal to 3.55k. Right. Next step that we need to do is we need to find the voltage TH, the voltage drop around here. Okay, and then that one will be VTH, and that will be equal with 22 times 3.9k divided by 39k plus 3.9k, and that's a flat 2 volts. Alright, next step is we can redraw the diagram, make it simpler and neater. So we got the voltage source here, the resistance here, and then there is a transistor here with the resistance here and the emitter resistance here. There you go. So this one has got 22 volts at the top here, 10k ohms. This one will be 2 volts here, and that will be 3.55k. And then this one will be 1.5k and connected straight to ground. Alright, so we already simplified the circuit a lot. And now this is really the calculation of a normal simple circuit. So then we can just do a loop here and a loop here. Alright, what we can do is we can do 2 minus 0.7 minus wait a second, 3 point, strange, it seems that I used 3.9 by mistake. Anyway, minus 3.55k multiplied by IB minus 1.5k multiplied by the gain. It's 140, so then IE will be 141 IB. Alright, so then therefore IB will be equal with 1.3 over, let's see here, so 3.55 times 3 plus 1.5 times 3 times 141, that will be 215.1, let's say k. Or let's just leave like 215k as well, that's good. And that will be equal with, so 1.3 over 215 times 3, that's 6.047, yeah, 6.047 microamps. Okay, so let's keep going. Now we can find IC because it will simply be the gain multiplied by IB. So that will be IB times 140, that's equal to 6.035, no, sorry, 047 microamps multiplied by 140, and that will be equal with 6.047 times the minus 6 times 140, that will be, no wait, 0.847 milliamps. Okay, we can also find IE, this one, which will be again IB, but this time multiplied by 141, that will be equal with 6.047 microamps times 141, that's equal with, can I like go back on this thing? I don't think it lets me, yeah, 6.005 times 10 to minus 6 multiplied by 141, and that will be equal with 0.852 milliamps. Alright, and now we can do the last part, which is finding the VCE, what we wanted to find in the first place, plus minus VCE, and that will be equal with 22 minus 10k, so 22 minus 10k times IC minus 1.5k times IE. Okay, and then that one will be equal with, so 22 minus 10 times 23 times IC, that was 0.847 times 10 to the minus 3 minus 1.5 times 3 times IE, that's 0.852 times 10 to the minus 3, and that will give us 12 point, yeah, that's equal with 12.252 volts. And since about right, since this is 22 volts. Alright, now remember this answer here, and we'll write it on the other side of the page because we'll do something different now. So our answer was 12 point, was it 5 something? No, 252 for VCE. Now, the interesting thing is that if you change the gain, if gain will be equal with 70 instead, but we applied the exact same thing, we still do 2 minus 0.7 minus 3.55k times IB minus 1.5k times 71 times IB, and that'll be 1.3 minus 3.55k IB minus 106.5k IB, and then therefore IB will be equal with 1.3 over 110. Wait, is not that, no, is it? Wait, 3.55 times the 3 plus 106.5 times the 3. Yeah, okay, I'll just leave it like that, k. And that will be equal with 1.3 over 110 times the 3, 11.81 microamps. 11.81 microamps. Alright, IC will simply be equal with IB times 70, and that's equal with 11.81 microamps times 70, and that's equal with 11.81. I'll just leave it here so you can see also. That's the minus 6 times 70. That would be 0.827, let's say, milliamps. And then IE will be equal with IB times 71, and that's equal with 11.81 microamps times 71, and that's equal with 71. That's 0.839 milliamps. Alright, now that we know these two currents, we can simplify VCE. So VCE will equal with 22 minus 10k times 0.827 milliamps minus 15k times 0.839 milliamps, and that will be equal with, so 22 minus 10 times 10 to the 3 times 0.827 times 10 to the minus 3 minus 15 times 0.839 times 10 to the minus 3. No, wait, that's too high. Let me check if I put them correctly. So 22 minus 10k times 0.27, okay, and that's milliamps, minus 15 times 8.37. Oh, I forgot to put the k on this one. Okay, that makes the difference. That's it, the 3. 1 point what? 10k. Okay, 22. That's good. 0.27 3 minus 15 times 10 to the 3 times, oh, there you go, wait, times 0.3 minus, okay, this is so strange. Why do I get this answer? So that's 10k, 22 minus 3, 15 times 839, that's 10 to the minus 3. This is way too low. 22 minus 10 times 10 to the 3 times 0.825 times 10 to the minus 3 minus 1.5 times 10 to the 3 times 0.836 times 10 to the minus 3. Yeah, I'm supposed to get something more along the lines of that, but this is a 9. It should make like a difference of 10 volts to be honest. And this will be a 7. There you go. Okay, that would be 12.4715, and this will be the VCE. So even though the gain is halfway through, this one had a gain of 140, this one had a gain of 70. Even though there's a big difference between those two gains, the answers are basically the same, because this one is 12.252. So I mean, it's basically like a difference of what, 0.0 something. So 12.252 minus 12.472. Yeah, it's just basically a difference of minus 0.22. Yeah, 0.22. So yeah, so this formation here will keep the voltage in control, even though no matter how much current gain comes from the top. Okay, so just keep the same voltage around this point here. Alright. I'm a bit tired. This one was a long one and I panicked at the end of it, since the calculator didn't give me the right answer. It started with like minus 20 and it went to like 1 volt until we got the correct answer, which was this one, 12.4715. Alright, this one was this exercise, and now seeing the next exercise. Now let's go to the next exercise. That was very similar to the previous one. Okay, so in this one we have a capacitor in here, but this capacitor won't do anything, and we also have two capacitors that don't do anything either. So mostly we'll focus on this part here. Okay, again, and remember, this one is more of a representation how you calculate when there's an AC input. So let's get rid of this wire here. We got the 20 volts, 20 volts here, 20 volts here. Okay, then we got IB going down here, IB, and IC going down here, and IE coming from the way here. And again, because this is DC coming through, then there is no current here or here. So this is something completely different that's helping with the AC output really than anything else. Right, so what we do, well, we got the two loops. We got this one here in this direction, and we got this one here in this direction. Right, so what we do, we start with the top. That will be 20 minus 0.7, the transition 0.7. We got this IB here, so that'll be minus 40k times IB, and then minus 1k times 100.01, because we got the gain of, oh no, we got the gain of, oh sorry, I wrote it wrong here, sorry about that. This is not it's not 140, it's supposed to be 100. Okay, that makes sense. 100 IB. Okay, now this one would be 19.3 minus that would be 101k, so this one would be simply 531k times IB. Therefore IB would be equal with 19.3 divided by 531k, and that will be equal to 36.35 microamps. Next off, it will be to find the IC, and the IC will be equal to 36.35 microamps multiplied by 100, and that will be equal to 3.635 milliamps. Next we'll find the IE. It's basically the same thing, but it's got 101, so that'll be 36.35 microamps times 101, that will be equal to 3.671 milliamps. Okay, now VCE, we can find the voltage, that will be equal to 20 to the minus 2k times I. Sorry about that, my sister walked in. Now VCE will be equal with simply, we got the 20 volts going from the top, the 2k here multiplied by IC, and then it goes down and we just take it away from 1k multiplied by the IE. Okay, and then therefore VCE will simply be equal with 20 minus 7.27 minus 3.671, and then therefore VCE will be equal with 9.059. Now what you may notice is that in this example here is not like the previous one where we had another resistor going down through here to balance it. So now if we make it in half, if we say that if gain will be equal with 50, then we redo the same calculation, that will be 20 minus 0.7 minus 30k, because this value here, the 1k, will get lower to 50k, IB minus 1k times 51 IB. Okay, and then it will get 19.3 minus 481k IB. Therefore IB will be equal with 19.3 over 481k, and that will be equal with 40.13 microamps. IC will be equal with 40.13 microamps times 50, that's equal with 2.01 milliamps. IE, it's equal with 40.13 microamps times 51, that's equal with 2.047 milliamps. VCE would be equal with 20.2k times IC minus 1k times, if you are confused about this, I'm basically just doing the same formulas here, but instead of using the 100 gain, I'm using the 50 gain. So it's nothing new in this side, it's exactly the same thing as here. K times IE, therefore VCE, it's equal with 20 minus 4.02 minus 2.047, so then VCE will be equal with 13.93 volts. Quite a big difference, a difference of about 4 volts here between the two of them. So yeah, this one is the circuit without the special resistor here, and also it's more in a AC format, and you may put a capacitor here because it will take 90 degrees away from the AC. So instead of coming at the phase of minus 180, maybe by putting the capacitor here would be a phase of minus 90 degrees either. But I do not know, I'm not sure about it, because as I said, I didn't really use transistors that often. I'll use them more this year. But yeah, that said, we'll go to the next exercise. It's in a bit then. Now this one, it's harder because we got multiple VCC, we got also VEE, and we got it in both sides. Now what do we do for this one to solve it? Well, let's take the blue pen and mark what we know and so on. So we can get rid of this wire here and have this side 20 volts and this side 20 volts at this point here, and we can also move this one down here. We can just ignore the V in and V out. Now the problem is like we got the VEE here as well, so we get rid of these wires here, and then we got minus 20 volts at this point, and we also got minus 20 volts at this point here as well. So what we end up with, and let me redraw it because it's a bit complicated to clarify it here to like see properly the circuit this way, is we get something along these lines. So there's the resistor, there's the source, and then there's the ground. And this one will be a VCC source of 20 volts from this here, from RB1 of 8.2 K. Then this one, it's in junction with this one, this RB2 here. So we create another resistor, another source, and another ground. But this one is the VEE that's connected to it. So that will be minus 20 volts instead of the plus 20. And that will be the RB2, the 2.2 K on resistor side. And then this one is connected to the transistor, and this side of the transistor is the side with the 2.7K, that's connected to 20 volts, and the downside of the emitter that's connected down here is the one that's connected to the EE, which is VEE of minus 20 volts, and that one will be the RE, which is 1.8 K ohms, and this one, let's call it the RC. Alright, so this is a more simplified form of this circuit here, but in here. Now we can even simplify this one even further by applying Thevenin's theorem. We can simply do this. Put these two buttons here, and the Thevenin's theorem here, put in them. Okay, so then we can calculate the total resistance RTH, and that will be equal with this one here and this one here in parallel, so that will be 8.2 K in parallel with 2.2 K, and that's equal with 1.735 K. Okay, next we need to calculate the source, but there are two of them. It's a VCC source and it's the VEE source, so don't think you get away from them. The VCC source will be calculated at this point here. So VCCTH will be equal with RB2 times 20, because 20 positive 20, over RB2 plus RB1, and that's equal with 2.2 K times 20 over 8.2 K plus 2.2 K, and that will be equal with 4.23 volts. Alright, so we calculate the first source, now we calculate the second one, which is the VEE. So then VEE TH will be equal with RB1 times minus 20 over RB2 plus RB1, because again we are this time for this VEE we are doing it at this point here. Okay, and that will be equal with 8.2 K times minus 20 over 8.2 K plus 2.2 K, and that will be equal minus 15.76. Right. And now we can calculate the total VTH. So VTH, that will be equal with the value of VCCTH plus VEETH. Okay, therefore we can write them like this. That will be equal with 4.23 minus, because it's a plus, it will be minus 15.76. So then VTH will be equal with the minus 11.53 volts. Alright, sorry. Now let's go to the next page, because we still have a lot of writing. Like, we only simplified, like what we did this far, it was just to make this circuit that started like this smaller and smaller until we get to the point that we can write it like this, with the source of VTH, which is minus 11.53 volts, and its resistance, which was 1.735 k ohms. And then it's going to the transistor here that goes up to here, and then it's got a source here of 20 volts, RC 2.7 k ohms, and then there's the emitter here that will go down and then to the ground, and it's got also a source here, and that will be the RE 1.8 k, and then VEE, that will be minus 20 volts. Alright, and don't forget about the gain, that's equal to 130. Now that we simplify the circuit to kind of like its simplest form, we can't really simplify more than that. We need to go to the solution of it to calculate it. And the first thing that we want to calculate is IB, the current IB going through it. So you can find IC and IE. So then that will be minus 11.53 minus 1.735 k IB minus 1.8 k times 131 IB, because this is the gain, we add 1 and then we get the current IE, so we can convert it to 131 IB. And then this is a minus, so it'll be minus and minus 20 volts, so it will become a positive. And let's not forget about the minus from the transition, which will be 0.7. Okay, now this we can rewrite it and simplify it, get the IBs together and everything together. So that would be minus 1153 minus 1.735 k IB minus 235.8 k IB plus 20 volts minus 0.7, and then it will be, if we do this calculation, then we'll get 8.47 minus 237.535 k times IB. Okay, and then therefore IB will be equal with 8.47. I hope I don't run out of ink now. 8.47 minus 0.7 from this one here, because we didn't do it yet. I'll put it here as well, 0.7 over 237.535 k, and that will be equal with 7.77 over 237.535 k, and then that will be equal to 32.71 microamps, and that will be the current IB. Now we can easily find IC and IE. So IC will be equal with IB times 130, and that will be equal with 32.71 microamps times 130, and that will be equal with 4.25 milliamps. IE will be equal with IB times 131, that will be equal with 32.71 microamps multiplied by 131, and that will be equal with 4.29 milliamps. Okay, now we can calculate VCE easily by just doing VCE equal with 20 minus 2.7 k times 4.25 milliamps minus 1.8 k times 4.29 milliamps minus 20 volts. Okay, hopefully you understand what I'm doing here and the formulas that I'm using. If you don't, then I guess you didn't watch the entire videos, or you just skip through it. But anyway, so yeah, after that calculation, we can rewrite it as VCE will equal to 20 minus 11.475 minus 7.722 plus 20, and that will be equal to 20.803. Alright, now that's the value for VCE. You may think that this is strange, how does it come that's over 20? But remember, you got the positive 20 here and the negative 20 here. If you're that way to do it, I guess we can find VC as well, because it's quite simple. VC, because it will just be the source VCC minus 2.7K multiplied by 4.25 milliamps. That's equal to 20 minus 11.475, and that will be equal with 8.525 volts. Alright, and that's the answers. This is everything we need to know. Okay, now there will be only one more exercise, and the last one will be an easy one, will be a breeze, just to like finish it off nicely. And this one is one of the harder ones because of all the voltage sources and the positive and negative voltages, and also because of the overall simplification that we need to do to get to a circuit like this one here to be easy to calculate through it. Because if you try to calculate through something like this, you don't even know where to start. It gets confusing, and yeah, everybody surely makes a mistake when it does it straight on this. So it's important to know Thevenin's theorem to like be able to simplify it to a point where it gets like this one here. But anyway, thanks for watching, and I'll see you in the next exercise, which will be the last one as well. Bye. Alright, now when you see this circuit, you may be like, well, this is very simple as well. We can apply Thevenin's theorem to these 2 points and get the answers that we want. And yes, you can do that, but you can also do it in a different way, and that's why we are finishing with a simple circuit like this one here. What you can do, instead of Thevenin's theorem, if you want, you can do mesh analysis actually. So you can say this loop here, and this loop here, and then this loop here. And this loop here will have the current I1, this loop here will have the current I2, and this loop here will have the current I3. Alright, so again, we need to find the voltage output from these points here between collector and emitter. So what do? Well, we apply a mesh analysis here. So we got the 2 volts, so that will be a 2 minus the 100K multiplied by I1 minus the 200K multiplied by I1 minus I2. So that was for the first mesh. Now we go to the second mesh, and there is no resistance at the emitter point, so that will make it a lot easier. So then, because if there was a resistance at the emitter point, then applying mesh here would be a lot more complicated. So then what we do next, we just write it, wait a second. Oh, I see what we did. Okay. Wait. Because I rewrote this one as this. I rewrote it as 100K I1 plus 200K times I1, this is times as well, minus 200K times I2. That will be equal to 2, and I simplify it before going to the next one, so that will be 300K times I1 minus the 200K times I2, and that will be equal to 2. So now we can go to this one, so that on to the second mesh. So this one is like mesh 1, this one will be mesh 2. This one will be 200K, this time will be I2 minus I1 minus the 0.7 volts from here, so 0.7, and then therefore we get minus 200K I2 plus 200k I1 minus 0.7, sorry, I don't have space anymore, that's equal to 0. Alright, so now we have the two simplest forms of them. So now we can just rewrite it here as 300k times I1 minus 200k I2, that's equal with 2, and then 200k times I1 minus 200k times I2, that would be equal with 0.7. So this one is actually conveniently placed for us to like simplify it into simultaneous equations, because what we can do is simply do this. So 200 minus 300, that will be 100k I1 equal with 0.7 minus 2, that will be 1.3. Therefore I1 will be equal with 13 microamps. But we are not interested in I1 alone, we are interested to see what goes through IB, which will be this here, IB. So what we can do next is to find the current I2. So we just do 300k times 13 microamps minus 200k times I2 equal with 2. That will give us 3.9 minus 200k I2 equal with 2. Therefore minus 200k I2 will be equal with minus 1.9, and then therefore I2 it's equal with 9.5 microamps, and we got I2 as well. And this I2 here, it's actually what IB is equal to. So IB it's equal with 9.5 microamps. And now we can determine IE by simply doing IB plus 150 the gain IB, and that will be equal with 1.4345 milliamps. Alright, now next what we do is to find IC. So then IC, that will be equal with IB times 150 equal with 1.425 milliamps. Alright. Next, we apply Kirchhoff's voltage law to actually find V out. So we take the 16 volts, so 16 minus 1k ohm, 1k multiplied by the current IC, which is 1.425 milliamps, minus V out here. There is no resistance or anything in here in IE, so it's simply 0, so it'll be 0. So then by 16 minus 1.425 equal with V out. Therefore V out will be equal with 14.575 volts. And it does kind of make sense because the current is very low here, the gain is quite big, but it's also a resistance here that makes the overall current smaller. And that's how you solve it if you want to apply mesh analysis instead of Thevenin's theorem. This will work because this is a DC circuit, but if you try to apply simultaneous equations or anything else in a DC circuit, in an AC circuit, then you will have quite a problem. Anyway, of course, unless it's made out of only resistors. If it's made out of only resistors, then you can easily apply the AC theory to it. But if it's got capacitors or anything else, then yeah, that would make it a lot more complicated to use mesh analysis. Anyway, thanks for watching, and hopefully I think I'll see you when I start next year and I learn new subjects. I'm not sure when I'll upload next, but until then, let's keep studying, I guess. See ya.